Okay, I think we here now have almost everyone. So welcome everyone. My first question to the audience, can anyone hear me out there?
Yes.
Okay, excellent. Good, yeah, welcome to the RAISE CoE seminar in July. It's heavy vacation period, but on the other hand, we also have this recorded for the YouTube channel. The topic of today is distributed deep learning, and we were elaborating on this a little bit already in the last June seminar when we talked about the HEAT toolkit, if you remember. And we have a couple of speakers today that go basically beyond the HEAT toolkit. We see that there are much more frameworks out there that do distributed deep learning, and basically brings us a couple of different speakers that have all in one way or another experience in that regard. So when we come to the agenda, I will introduce briefly the need really for distributed deep learning, why that matters in CoE RAISE. And then we have a 50 minutes presentation by Rocco Sedona, which really is an expert in the field, doing this for his PhD since quite a while now. However, is also very focused on the Horovod framework, and we will learn later that there are different frameworks. So still there's lots of experience to learn. However, here he gives more or less also a general introduction before he goes off into several distinct topics. Then we hear some experience from Atos, which would be quite interesting, from Dr. Marc Sergent. I hope I spelled that correctly. And we complement this then towards the end, essentially with some of the Jülich supercomputing experiences gathered by Marcel Aach. So in a way, this would be a topic which is very loaded, so we can talk about this a long time. And many people are really not sure, is it deep speed, is it heat, is it Horovod, or is it PyTorch, inherent scaling? So we will try to clarify and give some lights during the seminar on these topics. Just briefly about the speakers, Rocco Sedona, as I said earlier, is already a key expert in remote sensing since quite a while now, so really application engineer that just uses distributed deep learning to fulfill application goals. And he will talk about this, and I will make some examples in the introductory talk. He's a joint PhD student of the Jülich Supercomputing Center and University of Iceland here. Then we have Marc Sergent, who is basically a senior expert of Atos in the field of high-performance computing research and development. And it was a very interesting view because we are in the academics are always surrounded sometimes in some of these views, limited maybe in one respect to the academic world. So having here a speaker from the commercial world will also give us interesting insights in that context. Then just shortly about me, I'm a professor full professor here at the University of Iceland for parallel and scalable machine learning and high performance computing, but also research group leader at the Jülich Supercomputing Center in Germany since 16 years now. And more recently, I was also appointed at the Euro-HPC Joint Undertaking Governing Board member for Iceland here. So we try to bring you this topic closer. Just briefly to mention that this topic here and the webinar is also co-organized by the so-called EuroCC project and its NCC Iceland, the National Competence Center of Iceland, called EHPC, to host these webinars and to basically bring in some speakers in that regard. We have some simulation and data labs here in the University of Iceland, admittedly on a, let's say, smaller scale that you would find in Jülich, but still here and there very interesting research endeavors and all these different simulation and data labs. So from this, just to mention why Exascale matters for us, also a smaller university, if you want, or a medium range university has demands for scaling. And you see here our cooperations that we have with the Jülich Supercomputing Center in one way, hopefully reaching Exascale in 2023. And we have been part of the deepest projects before, the series of projects, but we're also part of the LUMI architecture. And if you look really deeply into the LUMI architecture, it's also a very modular supercomputing architecture, also moving towards petascale and then probably exascale later. So all of this is something which is a quite intrinsic topic, which cannot be covered by one webinar as a whole. We really pick here one peanut out, which is relevant for AI. But here I encourage you to look at this YouTube video here about modular supercomputing, which also shows a little bit how perhaps Europe can reach exascale in the 2023-2024 timeframe. So this is really all I wanted to leave on the table for the welcome. I would like to really directly continue to save a little bit of time with the basically need for CoE RAISE in essentially this deep learning strategies, why we need basically deep learning, why we need distributed deep learning in the end to also achieve the scalability. So I would like to, of course, recommend you, if you want to know more about CoE RAISE, to look on our website. A webinar like this cannot really have all the topics from RAISE covered. I will have a really high level introduction to RAISE and then go really into the machine learning deep parts where deep learning matters. So if you want to know more about RAISE, please go to our website. Just briefly, the overall motivation approach is to think about AI at scale. So we have simulation experiments like you see here, computation fluid dynamics that easily scale these days already up to petascale. And in a way, we can always scale more to have more details. We know turbulence is a phenomenon, for example, which is yet to be understood completely. And let's say a full DNS simulation of a wind turbine or so, or wind wheel, is still very hard to do. So in this sense, we need scale, but also AI technologies have been more recently used as surrogate models intertwined with basically those simulations or with other, let's say, interpretations of ensemble members, maybe where you basically kill first exam ensembles before they basically do, let's say, go into a direction which is not fruitful. So you basically can do a lot with AI technologies in this. And in CoE RAISE, we have been around many use cases, have seen that it's really used differently in all the different areas in order to predict, maybe replace, or even accelerate some of the simulation and experiments we are most interested in. I should say we focused mostly in the engineering domain. So you see we have two kinds of use cases in CoE RAISE, the compute-driven use cases that you see here around CFD, flows, but also about coding. And then we have basically more data-driven sciences as well, like fundamental physics from CERN. A lot of data gathering is taking place there. We have seismic imaging, remote sensing, and manufacturing, and different use cases really that create lots of data and want to analyze this data, which is, of course, another driver of the CoE RAISE project. So why we do this? We want to explore what it means to have AI at exascale. So what does it mean to have really scaling in all of these different use cases? And in previous seminars, and if you're interested, you can check out the CoE RAISE YouTube channel. You have seen we motivated this more and more. We said all these 9 different use cases here that you see generate in some form or another some data sets. And in CoE RAISE, what we try to do is to create AI models that kind of complement or augment this already physics-based models on the one hand side, or in the second part of the use cases, really work with the data and predict something in the data sets as well, which is of relevance to these use cases. But all of them have in common usually to really require much more computing power than a simple GPU workstation could afford. And of course, here I cannot motivate all of these use cases in detail. So again, each of the use cases are described on the different website elements of the CoE RAISE project. Much more focused on our discussions today, why distributed deep learning is exactly one of CoE RAISE objectives. And this is what you see here a little bit shown in this slide, where we try to get the software infrastructure and the hardware infrastructure right to serve these different compute-driven and data-driven use cases with some form of a unique AI framework. So we want to understand which of those AI frameworks, and we will see in this talk, there are many, many different tools and technologies out there. What are those technologies of choice that really scale and what we can really use in all these different use cases? And of course, the real setup of such a framework isn't clear. So that's why we have this research project. And that's why we co-design essentially this unique AI framework together with all the different use cases to understand this on the one hand, and of course to exploit as much as we can the, let's say, more or less exceptional hardware infrastructure we have underneath, moving towards exascale with really different interesting technologies in the future. So to come to this, does it really work? Intertwined HPC simulations and so on. You have here one example from one of my previous research where we had maybe 0 from 1,000 meteorological ensemble runs, which actually can be quite, use the scaling of high performance computing machines already. But what you do is you use with AI some technologies like particle filters or other statistics and other machine learning models like a support vector machine to understand and predict what of those ensemble members already lead to a wrong prediction. So with this, you can decrease the number of ensemble runs. You basically stop them early and recreate new ones from learning from the parameter sets. And this can be, of course, something which we call this full loops. On the one hand, you have still the need, of course, of the physical simulations based on numerical methods or known physical laws. On the other hand, you have these AI methods or machine learning, deep learning methods, which really use essentially then more data-driven approaches to complement this basically techniques. And this can be done, of course, it's, let's say, early in the area of machine learning and deep learning to be really intertwined with physics simulations. In the past, this was not really the case, but two different communities. I think, Andreas, if I could ask you to mute your phone, thank you. So, but the point here is really to think about how we can intertwine these worlds and what can we do to really support the development, because not every physical expert in CFD or in other engineering domains is really an AI expert. So we have to basically work together to achieve the Exascale goals that we have in Europe and beyond. And this could be in different formats. We're thinking about these scaling machine and deep learning codes, what we will have as a seminar today, but then also think about what are the new ideas of deep learning for time series analysis, perhaps like long short-term memory or gated recurrent units as an example. What data augmentation approaches are there? If you don't swim in data, if you don't have enough data, AI can be tricky. It needs a lot of data to train, to derive models from, and then also to validate them with validation sets. So in the sense here, data augmentation approaches can help. We benchmark what of those tool sets we have for AI work really well on HPC machines. And you see today also during the seminar, there are surprises. While some technologies like Horovod might be very, let's say, elaborated, often used, newer model frameworks or other model frameworks also could maybe scale much better. So that's something what we also will share later in this part of the contributions in the seminar. Of course, more on the end of the scale, you will see really something like we call auto-ML techniques or semi-automatic ways of performing hyperparameter tuning for neural architectures, really searching the architecture of those deep learning networks, which is still not fully understand to do automatically and often is really application specific. So let's say a big set of what this AI framework should deliver and also complement. You could think also about pre-trained models when you think about transfer learning, which is also an interesting technique today. But really in this seminar, we would like to put the spot now on one of the key aspects of this AI framework that we're going to develop and that we prove for, let's say, scaling, which is here really shown as a kind of set of technologies. We have heat, we have Horovod, we have PyTorch, deep speed data, very much common and known ones. And here the question is now, what of those technologies, should we basically have as a unique AI framework? Maybe narrow down the technologies, or more accurately speaking, maybe proving that some of those AI framework techniques really are able to scale at exascale, which is not trivial. And we will basically see this always towards the end when we have the seminar, where Marcel then also shows some scaling. And I think also Atos has some elements to share. So when you think about these distributed training frameworks, here again, a slide we had from the last seminar here around heat in June. Here you see there are a lot of these technologies around. Of course, you could see today we maybe can reduce this a little bit when we say that multi-GPUs is, of course, something we are very interested in. So you will see that this seminar also focus a bit on PyTorch, and we will elaborate very quickly on deep speed, but then also think about what is done with Horovod. So in a way, you see more and more of those techniques coming online are available, and we have to analyze and see what are the best ones in terms of really scaling on HPC machines. So again, this will be on YouTube soon. So here, when we come back to this particular slide and think about, can we do really with AI exascale? So when everybody in AI is using GPU workstations, so how in the world should we do essentially then the scaling and how we do essentially then basically any benefit from this or get any benefit from that. And here you see examples essentially from one of the researches we performed with the Europe 1 supercomputer on Joules, where really get the time per epoch significantly down when using just multiple GPUs together. And this makes this distributed deep learning, right? We don't want to use one workstation with one GPU, or we want to not have four GPUs maybe exploited in one node. We want to go really beyond different nodes in a HPC machine. And this is something where you need specific tools actually to help you with, and we will focus on this particular seminar exactly on those. That this can be done is shown in many different publications today. So you see here examples from my own research and basically also from my PhD students. We're scaling up a ResNet 50 to 128 GPUs by now. This also works well more recently in A100s. You don't have to take just V100s here. Of course, this is something where there's current developments and frameworks, there's current developments always in different accelerators technologies, which is quite interesting. So example of Horovod is something we will start a little bit with maybe, and this was done as Horovod, but it does not mean that this is a technology of choice necessarily. So this was been using now by many different research groups over many years. It's a data parallel distributed training tool. We will see more on this in Rocco's talk when he talks about it. But the key point is we can share here lots of experience. We have done and used that since quite a while now. So this is also the one aim of this particular example here that we have in this webinar. And also Rocco, as you see from the publications, is here really the driving force in his PhD analyzing this with a particular idea also to look on the challenges of distributed deep learning. And you see that a little bit elaborated here, that it influences a little bit how you form the batch size of how much accuracy you get out. And of course, we want not scaling just for the scale's sake. We want to scale for still, getting a nice speed up and getting the training time down, but to keep the accuracy, or at least a modest accuracy, which is comparable to a, let's say, single node run, for instance. So there's no point in having, let's say, the speed up of AI perfectly, while let's say, the accuracy drops significantly. So this is the key challenge, and this is one of his research, and he will elaborate in his presentation much more than I will do here. So basically now fasten your seatbelt. We will look into Horovod a little bit, but also don't forget to see the view of PyTorch, which will come later in the seminar today, to really explore how that is done, what techniques are used. You see here, Horovod, for example, uses MPI or reduce, a very traditional technique in HPC using the message passing interface for the exchanging of different, let's say, information across nodes. But we have to ask ourselves in RAISE and also in the community, is this really the preferred solution that scales very well? And we have some insight there to share later. So when we ask ourselves why we come to this, basically this is just coming out of the process of RAISE. I will not go further deeply into it. We had fact sheets. We had then something we called an interaction room where we dynamically go through different teams and all in one form or another identified those frameworks. So we said one wants to have TensorFlow with deep speed, perhaps one want to have basically TensorFlow, but prefers more rather Horovod with it. And so different PyTorch examples have been around in the discussion. So in the end, through all this process now in CoE RAISE, which runs for half a year right now, so we already have identified there are many different AI techniques that actually are existing, and we want to speed them up with this, let's say, different frameworks. Of course, here in the short of the time, again, I cannot go into all the details. That's why I want to point you again to our YouTube channel. Here goes the marketing again. You will find lots of interesting seminars for the CoE RAISE context, also the interaction room methodology itself that we apply in the project. But of course, the key message to take away, I think, is really that when we go through all the different use cases, we have analyzed the desires, we always find the requirement for scaling up the deep learning in the architecture canvas. What technologies of use here is a big question for us. What scales very well, especially towards Exascale, is a question. And the seminar will go a little bit towards this to elaborate on this. When you see where it fits in terms of the AI modeling, you see here a little bit that PyTorch, DeepSpeed, Horovod, and all of these frameworks would be still in the learning algorithm fashion. So it's not some magic that you can apply there. So you still have to learn the algorithm, taking some training examples and using your hypothesis set, which could be support vector machines, could be deep learning, could be whatever else, but you still have to learn and basically train the AI system over time to come to your final hypothesis here that hopefully gets the model right and actually have a little error measure. So basically a very accurate model, hopefully. But in a way, you get essentially two impacts out of this. The first one is you accelerate the training itself. So that's, I think, pretty clear when you do it distributed. As we see, the speed up is nice. But the second impact is with this, if you think clearly, that never an AI model is finished when you do one run. You see here very well in this slide, all of these are hyperparameters that we have to choose, so that we have to rerun with different configurations. So with this, you have this kind of multiplied. So the speed up that you have through the distribution, which is one impact, you actually multiply by the second impact by having these models run not one times, but maybe 100 times. And this is really all I think I wanted to leave you on the table for you. We do this, as I said, in the remote sensing area. If you want to know more about this in very detail with a particular focus on Horovod, perhaps you're welcome to use a more elaborate, let's say, lecture series that we cannot provide here as a small seminar. You see here in this following YouTube channel from the University of Iceland in collaboration with FZJ, you have Rocco again, but there he talks 2 times 40 minutes, which would be too much for the seminar. So here for you, we carve out the details, augmented with some news in this 40 minutes that he will present, or 50 minutes today. But if you want to learn more, really lots of details, firstly, Rocco is available, of course, for questions later, and we will basically give him the questions if you put them in the chat later. But also here's a lecture which is maybe very interesting for you. All right, so with this, I'm finished with my talk. Now I have to say that Rocco, when we set the date here together, was already on vacation. So he provided us a recording. And I think it's still very valuable to show that because essentially it picks out the details of all these different elements of these lecture series I provided basically as part of the lecture series. And we will now listen to his recording, which really puts an emphasis on the topics we need, in particular in CoE RAISE, and also as part of the seminar. So just to check if you can really hear the sound of him, that would be good.
Hello, everybody. I am Rocco Sedona, and for whom does
It's okay.
Do you hear it? Okay, excellent.
Yes, it's
so
okay.
Perfect. So then we hear now distributed deep learning by Rocco, who's really an insight in the field. It's a little bit an introductory lecture, and then we will have it complemented with some experience afterwards.
Doesn't already know me. Hello, everybody. I am Rocco Sedona, and for whom doesn't already know me, I am a PhD student at JSC and also at the University of Iceland. Today, I will give a 40-minute talk about distributed deep learning. I will start with a roundabout on what distributed deep learning is and why we need it, and what is the motivation to adopt this technique. Then I will briefly present some of the most widely used frameworks, and I'll also briefly talk about one of the applications which we developed in our group. As from what I understand, most of you are not newbies to deep learning, I will just skip the introduction, which I usually give on backpropagation and all that stuff, which you most likely already know. So, yeah, what is happening in the in our field, in the field of deep learning in recent years? What has been happening is what you can observe in these figures. So models are becoming increasingly bigger, so they feature an almost exponentially larger an increase of the number of parameters. So you can see, for example, that some years ago, we had models in the order of the millions of parameters. For example, RSNet 50 has around 20 million parameters, if I'm right. And you can see that then at some point around 2018, we reached the threshold of the hundreds of million of parameters. And now the big models like GPT-3, which actually isn't listed here in this figure, is in the order of the hundreds of billion of parameters. So imagine how much memory, how much computational requirements are now required to train these very large models. So, but why are models increasingly bigger? Well, the fact is that it has been noticed that at some point, if you keep increasing the model size with respect also to the size of the data set, the predictions, the accuracy that you can get from deploying these models can beat the accuracy obtained by smaller models trained on smaller data sets. But again, it's very important to remember that obviously bigger models require to be trained on bigger data sets in order to avoid overfitting and to keep very good generalization capability. So what is the direct consequence of this need for of the rise of big models and trained on bigger data sets? The consequence is that obviously, as I was saying some minutes ago, the need for more resources, so for both in terms of memory and of computation, is really important and is really demanding. So here it is again about this generalization about which I was talking. The conventional view, the standard view, is depicted in the left figure, where you can see that it was noticed some years ago that at some point, if you trained your model too much, then the loss or the risk here in this figure of incurring overfitting would increase at some point. So it would mean that if you keep training the model on the same data, at some point you'd see a divergence between the training loss and the test loss. This is something we are pretty, we observe quite often, as you already know. But actually, much more recently, these concepts has been actually discussed and debated, and it has been noticed that given a large model, but also a very large data set, what happens is that it's true that overfitting, well, it's true that loss at some point, the test loss goes up and reaches a peak, but then if you keep training, the test loss goes actually much lower than the plateau it reached in the classical regime. And what happens is shown again in the right picture, and it means that once you reach this point and you keep training, actually you can reach much smaller test losses. And this is very interesting, and this gives a reason of why now big models trained on big data sets are used. So there are now I will go to a different part. So the first two slides were about motivation, and while here we enter more the concepts of how we can distribute training of a deep learning model. So there are multiple families of approaches, and two main ones are, well, The two are data parallelism and model parallelism. Then there is a third known as pipelining, but it is a bit of a different story, and I will try to explain why. So I will start with data parallelism, which is actually up to now the most widely used because it's also a bit simpler to adopt compared to model parallelism. So model parallelism actually means just this. Given that you have a model, you replicate this model on multiple GPU devices, for example. So you replicate the same model, but you give as input to the different GPUs, you give different chunks of data as input for training. So it means that during training, the GPUs will see different data, will be trained on different data, but at some point in the process that you can see here in this figure, the gradients are computed locally on each device, but through some operations that can be, for example, an MPI or reduce, or a nickel and CCL or reduced, if you use Horovod, you average these gradients. And once you do so, you can make so that the update of the model is consistent on each GPU. So you end up batch after batch or iteration after iteration with a consistent model on each GPU, even though the input data that each model sees is actually different. So this is the basics of data parallelism. I will talk about it more when I will speak about Horovod. The other approach is called model parallelism, and it is different in that instead of replicating the same model on the devices, you actually split the model, and you load different parts of the model on different devices. So, for example, you might have the first layers on one device and the second, the final layers of a model on a second GPU. So the problem compared to model parallelism is to data parallelism is that model parallelism is much more complicated to adopt, and you can easily spot the reason why it is that. Reason is that obviously you incur in a much higher number of interdependencies between the layers, if you imagine how big a deep learning model can be. And obviously, to deal with that, up to some time ago, researchers had to really design their own frameworks. Now things have been changing since last year, as DeepSpeed is actually providing a very interesting API to do so. But again, this is something quite new. So yeah, not still state of the art, I would say, not still used by many researchers, unless you talk about Google Brain, OpenAI, and the really, really big ones. So there is, as I was saying, a third approach, but it might refer, actually, it's more a term than approach, because it might refer to different things, and it's pipelining. So pipelining can either refer to the overlapping of computation between one layer and the next as data become available. So in this sense, it is something more related to data parallelism. Or the second definition is to partition the model according to the depth. So you kind of split the layers, as in my example of model parallelism. And in this sense, again, it would be more related to model parallelism. So when you read pipelining as an approach for distributed deep learning, always try to understand what the scientists are referring with that term in that specific publication or book or whatever, because it might refer to very different things actually. So from now on, for some slides, I will mostly talk about data distribution as an approach because I'm more familiar with it, but also because I have, I mean, as I was saying, up to now, it has been the most widely used. Still, I will talk about model parallelism again later on when I will present what deep speed is. So before we go ahead, it is very important to recall these concepts of what batch size, of what a batch size is in the realm of distributed deep learning. So in distributed deep learning, the global batch size is considered to be the local batch size multiplied by the number of devices that you have. Given that the local batch size is the batch size on each GPU that you are training on. So this is a very important concept because the main challenges of distributed deep learning of data distribution, but I would say in general of distributed deep learning is from a scientific point of view, let's keep aside the technological issues for now, but from a scientific point of view, the problem is, I would say, twofold, and the problems are these. So, and are very much related to the batch size. So it has been noticed that once you train with very large batch sizes, you might incur stability issues during training. So we would talk about optimization difficulties during training. Actually, these can be solved by many I would say approaches that we can put to work in order to avoid these kind of optimization difficulties, and I will present some of them in the next slides. But then there is a subtler and trickier problem to solve, which is the generalization gap that is caused by sharp minima when you train with large batch sizes. And this problem has been addressed by some researchers, but still, in my opinion, is still debated how much this is still presenting problems. There are new optimizers that try to solve this issue, but the research is still ongoing. If you want to know more about this issue of sharp minima, I would suggest you to look at what I put here, the reference 6, if I am not mistaken, which is an old paper from the 90s of one of the pioneers of AI. He is a bit less known maybe to the large public compared to Hinton, to LeCun, and to those. He is Jürgen Schmidhuber, and he is the director of the AI Center of the University of the Italian Switzerland. And in this paper of the mid-90s, he provides a mathematical formulation of why this problem of sharp minima happens and what it means. And if you are into math, it's a really interesting read. Obviously, we will not delve into that now because, yeah, this is only a 14 minutes talk. So again, well, there is another problem that is rather not scientific, but technological, which is the scalability of our model. But it is more related to the choice on which machine you deploy your model on, which is the library that you're using as a communication backend, and these kind of stuff that are also very interesting anyway. And so obviously I will try to answer your questions. In case you have, you can send me an email or whatever. We can open to talk about this, obviously. But again, about batch size, which is the scientific problem, I will try to show here in this figure what happens. And so what researchers noticed some years ago, if you see, is that at some point, if you use large batch sizes, global batch sizes again, and very standard optimizers like SGD, stochastic gradient descent, what you notice is that you can't speed up training anymore. You can't decrease the number of steps of iterations to reach a certain accuracy on the validation set if you keep increasing the batch size, the global batch size. So it has been noticed that this behavior happens usually somewhere around 2 to the power 13, which is in fact a batch size of 8K, so 8,000 samples. And this is a very important thing to remember when dealing with deep learning, with distributed deep learning. So what it means is that, as you can imagine, this would limit us a lot when it comes to distributing our model on a large number of devices. And so it's very important to understand how to tackle this issue. But I will again speak about that later in the slides in the presentation. And while these two slides that I'm presenting now are more related to the how the synchronization of the optimization is done, in the sense of rather you do it asynchronously or synchronously. So the big difference is that obviously in an asynchronous optimizer, here is SGD just for simplicity, each model is trained iteration after iteration with different input data, but the models exchange the gradients only at some random points in time. While in a synchronous SGD, every device is actually waiting after each iteration to exchange the gradients. And obviously the consequence is that synchronous optimization might be blocked if there are some devices that for some reason are slower. But good thing is that the convergence of the training is guaranteed. While in asynchronous SGD, what might happen is that at some point the models diverge on each device, diverge so much that they exchange meaningless gradients in a way, and so the resulting model is not really is not really good for generalization. Another technological aspect that is important, especially when we will talk about Horovod, is to remember what happened before Horovod to do data distribution. And what happened before Horovod was that most of the frameworks use technology known as parameter server. So there was a central parameter server, a central worker or process that took care of collecting the gradients from all the other devices and then perform the average or the reduction, whatever it was, and then send back to each worker the gradients. Obviously, this had the drawback that it relied on a single process to do this collection and then redistribution of the gradients, which was subject to, I mean, in case of, for example, communication issues, it would pose a serious threat to the speed of the training. But I will talk about this later and how this technological issue has been tackled by Horovod. Rather, I will on the next 4 slides focus again on the scientific a problem related to the batch size and what researchers have proposed to overcome these issues. So a very important hyperparameter to select when we do well in general for deep learning, but also it's very crucial for distributed deep learning, is the learning rate and how to set it. So given that you have your small or original, let's call it, learning rate for your non-distributed problem, you have to decide at some point which is the learning rate you're going to use when you do distribute your code. So some researchers some years ago, Goyal and others in 2018, if I recall correctly, proposed this way of selecting the learning rate when you distribute the training. And what they proposed is a linear scaling policy, so that you just scale your original learning rate by the number of GPUs that you are using. And this is motivated by this formula related to the stochastic grand descent. And in fact, if you look, what I want to do is to, in fact, make so that the training with a single but very large batch size, well, the update of the weights with a single but very large step is equal to many iterations, many updates with smaller batch size. So in order to make this second and third formula similar, well, the same, they propose this linear policy to scale the learning rate. However, this is based on a very strong assumption on the gradients. As you can imagine, it might be, and it's actually can happen that the gradients of a larger step is actually different from many, can be very different from the gradients with smaller batch sizes. So what other researchers later proposed is taking into consideration, instead of the formula of the update, to take into consideration the covariance matrix of the weights. And in this way, they proposed a scaling of the learning rate, which is proportional to the square root of the batch size instead of a linear policy. And actually, they show that especially with larger batch sizes, these can be beneficial because the linear policy was a bit too aggressive, and actually at some point causing an optimization issue. So the training started to sometimes diverge, especially in the early phases of the training. And in fact, also for this reason, another approach which is very widely used is the so-called warm-up, which is a strategy to use smaller learning rates at the beginning of the training. There are generally two types of, warm-up: the use of a constant warm-up for some epochs at the beginning of the training. And I would say the most widely used one, that is the gradual warm-up. So you epoch after epoch or iteration after iteration, depending on how you are training your model, you ramp up the learning rate. And this has actually been shown to be very beneficial to stabilize and make the training in the early stages much more steady and avoid optimization issues. So but this is a very wide known and used technique. Other approaches that are used also in combination with the other I presented before are the adoption of newer optimizers. One of these is LARS. So this layer was adaptive rate scaling, which is nothing more or less than SGD, but it's a stochastic grand descent where the learning rate, layer by layer, is scaled by the magnitude of the weights divided by the magnitude of the losses, of the gradients, sorry, of the gradient of the losses. And the researchers actually showed in their paper that in this way they could reach batch size up to global batch size up to 32K and also bigger on some applications. There are also other newer optimizers, for example, LAMB, which is similar to the concept of LARS, but it's based instead of on SGD, it's based on ADAM, so it's even more adaptive in a way. Then there is, for example, NVLAMB, which is the NVIDIA implementation of LAMB, which is offering actually something a bit more advanced in the when it comes to the pre-normalization of the gradients when you initialize the model. Then there are others like Novograd, which I recently used also for an application of ours. But still, the research question on whether these optimizers are really needed is still open and debated. Very recently, researchers from Facebook, if I'm right, suggested that actually, if you allow SGD or ADAM, so I would say rather standard optimizers to be trained with an hyperparameter optimization, an hyperparameter search, actually, they showed that using an hyperparameter search, they could reach very good accuracies, even with very large global batch sizes. So what they argue is that it might be that it's not the new optimizers, LAMB, NVLAMB, or LARS, that provide an advantage over the traditional ones, rather than the hyperparameters that are used, like, again, the learning rate, but also the weight decay, the momentum, and all that stuff. So, so I'd say that this is something still very, very debated. And if you are into that, I really suggest to read, obviously, the papers about Lars Lamb, but also these very new paper on how to tweak SGD and ADAM, some more traditional optimizers, because it might give you many insights on this issue of global batch size, which is, again, one of my research interest anyway. So again, once again, I tell you that if you want to discuss this, I'm open to that. But then now I will talk about Horovod, which is one of these frameworks that is used to distribute the data distribution. So there are also other frameworks or also built-in strategies in TensorFlow and PyTorch now. But what Horovod has of why it is interesting is that it can be used on top of those deep learning framework, and it's very flexible and can be implemented with not more than 7 lines of code. So Horovod is very interesting also because it's a decentralized framework, so it doesn't rely on a central parameter server. Rather, it uses a distributed ring or reduced. And to do so, it uses the primitives provided by MPI or Nickel, depending on how you set it up. So if you use Nickel, it can speed up the training, especially if you use a configuration where you have multiple GPUs on a single node. So where you can use NVIDIA NVLink technology, and Nickel is very optimized for that. And I think that instead, if you use a single GPU on multiple nodes, then the difference with MPI might be a bit less. But that's just what I found out, and I mean that's just my opinion, obviously. Yeah, I want to mention the fact that also, again, TensorFlow and PyTorch have their own strategies, and nowadays they're really, really similar to that of Horovod. And in fact, I talked about this with Morris at our course at his course in Iceland, where I presented a lecture on that. And yeah, you also notice that that there is a sort of convergence that always happens at some point with technology. So the frontier is very fast-paced, but once the technology is well established, then I mean it's adopted by many different providers, and that's what is happening also with data distribution. While with model distribution, again, we are a bit lagging behind still, as it is a newer, very much newer API like DeepSpeed to speed up. Well, actually, to be able to distribute the model on multiple devices. But let's see what Horovod does. So it uses again the ring or reduce, so doesn't use the central parameter server. And if we follow the life cycle of one of these bricks, so we have, for example, here 3 workers, 3 devices, and we have these bricks of data, which might be our gradients that we want to exchange. And what this algorithm does in 2 steps is this. So there is a share phase where each worker sends a chunk to the following worker. And then there is a reduction that happens that in this figure here is actually an addition. So if you look at the values here in the first brick, 513, and in worker B, 811, if you look at the sum of these 2 bricks after the exchange, in fact, is this resulting 1324. And this is done by each worker, which exchanges one of its bricks, and it's done until every brick has been exchanged. And then once what happens is that at the end of this this process, the each worker will have 1 complete reduced brick, and so it will have to exchange it again with all the other workers, but this time without the reduction step, so that the workers have, all workers have a consistent model. So as I can understand, my explanation can be a bit confusing for you. I really suggest that if you are interested in that, you look at this very good explanation with a video, an interactive video, which which can help you visualize this. And again, what is good of this algorithm is that getting rid of the central parameter server, actually the number of communications that are performed are actually less than using a central parameter server, and it's shown by this formula here. So you basically get rid of of the number of process. So it means that you are independent. You can, in principle, grow the number of GPUs you're training on without incurring significant communication issues, and that's very interesting, obviously. So there are some ways Horovod, you can tweak Horovod to work better. So Horovod offers these flags to tweak it, in fact, and to decide to adopt some thresholds to group the gradients for exchange, and also to decide when to exchange these gradients. And I'd say that this is a very interesting feature that Horovod offers, and you can play around with it. And also you can set automatically some of these. You can tell Horovod to learn by itself these the optimal values if you set these flags. And I would say that in general, it's a good practice to, at least for the first time, to play around with it. I will present now an application that I developed with our group, with Gabriele Cavallaro, which is a remote sensing application. So what we did is to train a large ResNet 50 model on patches extracted by Sentinel-2 tiles on the very big EarthNet. The name is self-explanatory remote sensing dataset. So what we did, why we used a ResNet 50 is because although it has been presented some years ago, it is still very widely used. If you think that even now it is used by Google Big Transfer, so it means it's still a very advanced model. And what we did is training it on multiple GPUs up to actually now much more than 100. Now we even reached 200 NVIDIA GPUs. And adopting a set of the optimization of the practices that I showed in the earlier slides, actually we could reach good accuracy up to a batch size of 8K, which is, you might wonder, okay, it's not very big, but still, since we are dealing with a data set which is very complex, and it's a data set which has multiple labels for each batch, actually, we were pretty satisfied by this, and we are still working, obviously, on improving that, and we are now reaching some better results with 16K, but still, this is an ongoing research for us. And obviously, there are many other interesting aspects that one might dig into while dealing with this. As I was saying, we managed to scale on 256 GPUs on the new A100s of the US booster. But also, I mean, there is a lot to test, like even newer optimizers, or as I was saying, hyperparameter search, or for example, also neural architecture search. And there is really a lot to do on that. But again, after data parallelism and my application using Horovod, I will end my presentation with DeepSpeed, which is a much newer framework presented last year in May 2020, developed by Microsoft, which actually provides an API which can be used, unfortunately, only with PyTorch and not with TensorFlow up to now. And what it does is that you can do both data parallelism, but also model parallelism and pipelining. So the combination of both, and the slide of the data and the model of the layers of the model as you like, and these with a very simple API. I tried it myself, just the examples provided by Microsoft. I didn't really use it on real applications developed by myself. And in fact, Marcel, who should also talk today, I think is starting to have a look at DeepSpeed, if I'm right, and we are starting to have a look also together with some application of remote sensing. So a very interesting feature, except providing the API for data distribution, model distribution, is that DeepSpeed comes with this optimizer for memory. It's not optimizer in the sense of the update of the gradients. It's here something very, very different. Here, optimizers refers to memory, so to the offloading of the memory to CPU to train the models, and they showed that in this way they can train much larger models than it was before possible. And so this zero, now I think they reached they also released the 0-2 offloading that is even more powerful. Another feature that is very interesting is the sparse attention kernels that come built in with DeepSpeed. Why is this interesting? Because the very successful models for neural architecture, for natural language processing that are used nowadays are the so-called transformers. So in vision, we are still a little bit behind, but visual transformers are now starting to become available. And they are based on this concept of getting rid of convolutions and using instead the attention. So to have a sort of local, a way of locally encoding information. So this is attention, and DeepSpeed comes with a very well-optimized sparse attention with many very well optimized sparse attention kernels. which can be again local or capture global global interactions, or also random masks. So DeepSpeed also provides some optimizers in this way, in the sense of real optimizers for gradient update, for weight update through gradient, more correctly. And one of these is the 1-bit Adam. And now I think they also released LAMB or LARS, their optimized version. So in this way, they managed to significantly speed up the training, reducing the communication volume of the gradient exchange. And yeah, I'd say that that was it about my very small presentation and brief presentation about DeepSpeed. And again, I'm not super experienced with that. I'm much more experienced with Horovod, but still, I think it's very interesting to always look into newer frameworks and things, as this field is keeping evolving at a very fast pace. But I want to conclude with these two last slides. My presentation explaining why, again, giving them a real motivation of why these frameworks are useful. So what happens is that GPT-3, as I was saying, a model with almost 200 billion parameters, you cannot imagine of training it on a single GPU because it would take just years. That's unrealistic. So one obviously has to rely on some way of distributing these the training of these models, and this is why we need these families of approaches, so model and data parallelism, and also the frameworks to actually implement these. So this slide actually comes from a presentation I gave in a course of Morris at the University of Iceland, which gave the motivation of why actually working on HPC machines, even though we know that might be annoying sometimes, loading the correct modules and so on, but why this is very interesting for us researchers. And you can see here I put an example of how many parameters has GPT-3, and of the prices of some resources of Microsoft Azure, of the GPUs. And if you make some very easy calculations with this formula, you would see that actually training just once this model would become really difficult for us researchers to pay. 3 million euros, I think it would be even more than every European project we can get, or not, Maurice, tell me. But I guess that they wouldn't like us to spend 3 million euros just train the model once, and then think about, okay, maybe the model overfitted, maybe you have to train it many times. So we couldn't make research in this way. And that's why, in my opinion, it's also very interesting to use, to be able to access HPC resources. So even if you sometimes are discouraged, I suggest to keep trying, because at some point you will really be grateful for that. But jokes aside, I want to say also that there is a lot of ongoing research. Again, it's a very fast-paced environment and field. There are also frameworks developed by public institutions. For example, HEAT, which is developed also by Helmholtz Association, so also by some colleagues, which provides at the moment also some ways of doing data distribution with Python support, and also many other features. And Tarantella, pardon my Italian accent, which is very similar but provides the same the support for TensorFlow, but it is developed by the Fraun author. So yeah, but there is a lot of research ongoing, and as I was saying, most of the technology that is related to data distribution is now well established, while for model distribution it's much more at the frontier. So to conclude, what we notice, if you look at the bigger picture, is that the trend is to make, in general, distributed deep learning much easier, providing this simpler API to adopt, like Horovod, like DeepSpeed, but also the built-in solution of PyTorch, TensorFlow, MaxNet, and so on. But now, not only frameworks are provided, but some companies are starting to provide a product from the hardware to the software to the library solution. So a complete solution to train the models. An example is, for example, this Samba Nova, which provides an environment complete of everything, and they call it, if you know the for example, infrastructure as a service and all the terminology of cloud, they propose something different, which is known, they call data flow as a service. And this might be something interesting to look at. I want to thank also the colleagues at Helmholtz AI Consultants at JSC, because, well, some of the slides were done also with their help, and also with their help we are able to always keep our algorithms work better. So thanks to them as well, and obviously thanks to all my team who supports me and supports my research. And the takeaways again that I want you to have is that, okay, the APIs are making things easier, but the frontier is very fast paced. So if you look at, for example, DeepSpeed, at the very new feature, you would find that, okay, the support is a bit lacking and all that stuff. But if you look at Horovod, you see that it's very stable now after some years. So always remember to, when you want to adopt some of these frameworks, also to understand where you are in your research. So whether you want to try something new or whether you want a very stable, very well documented and well-known solution. So always try to also keep in mind this. So I left also the bibliography, the references. There are many interesting things. If you're more into the math or more into technology, I tried to leave many. And so I want to thank you for the attention, and I'm really sorry that I cannot be present today, and I had to record my my presentation, as I will be traveling to an area where unfortunately internet is not the best thing. So thanks a lot for the attention again, and I will now stop the recording.
All right, that gives us the opportunity to come back. My question is to the audience, do you still hear me?
Yes.
Okay, good. Yeah. So I think Rocco's talk was very interesting, especially in the light of the fact of this fast pace that he mentioned in the end. And I hope it was a good takeaway message for you. I invite you to put lots of questions in the chat. He cannot be with us today, unfortunately, but he is able to respond to questions. So if you have questions already, we have some discussions perhaps at the end of the seminar. But also, please, if you have questions right now, put them already in the chat. We will pick them up and send you then the email back once we talk with Rocco about it. So we have 2 more talks to come in the seminar, and it's basically my pleasure to have firstly a speaker from Atos, but a little bit neglected in my overview also Marcel Aach, who was also stepping in then basically last minute of giving basically hot details about how basically some research is going on at the Jülich Supercomputing Center. So we have these 2 talks now before we enter the discussion. So while basically we entering in the next talk, I have to ask if Marc is maybe online right now.
Yes, I'm here.
Oh, excellent.
Hi, Ron.
Good to have you. Hello. As you hear, he is from Atos, and I would invite you to share your screen right now. And start the presentation. You have 20 minutes, a bit more, a bit less, doesn't matter. I would otherwise call in when it takes much more longer time, but please take the stage, and thank you very much for talking.
Okay, so hi everyone, and thank you again, Maurice and Gail, for inviting us to this seminar today. So my name is Marc Sergent. I work with a lot of people that you see here on the bottom of the screen at the runtime and performance for users team at Atos. So first, I will introduce you first my team to tell you some of the context of our work, and then I'll share with you some experiments that we made with distributed AI on both CPU and GPU clusters, and with a specific concern about I/O capabilities. And then we'll have a small question and answer, or right now or afterwards. I don't know what Maurice will prefer, but I will be open to some questions at the end, I think, if I'm on time. So first, my team, which is runtimes and performance for users. The main thing to understand here is that we came from the HPC community more. Our goals as a team is to bring the best performance of the runtime system software stack for HPC users. So mainly we are working on an enhanced flavor of OpenMPI in my team, which is the Bool OpenMPI, and other tools to improve the performance of applications for our customers. But the main idea here to retain is that we are from the HPC community. So we discover the AI domain quite recently, in fact, since we started to work on this topic only in May 2020. So our goal on that topic was to propose solutions to get the best performance on AI workloads for HPC clusters in general. That's why we will talk about also running AI workloads on CPUs, distributed AI on CPUs, to tackle HPC legacy clusters, which are often really CPU based right now. So that is what we are interested in. So this talk will be mainly on the results and of our investigation of primary investigations about performance of AI runtimes on HPC clusters, so that we can give you some infos on what we can expect from HPC clusters, and what we can expect for future AI workloads on such clusters. So first, I'll talk about distributed AI. So on CPU clusters, like I said, we are really interested in CPU clusters because a lot of HPC clusters are still CPU based. And for HPC AI conversions, we need AI workloads to be able to run efficiently on CPUs as well on GPUs, because not all data centers can afford to buy new GPUs only to run AI workloads, but want to try out HPC AI conversions on in their applications to see if they can gain a benefit from it or not. So what we'll share today is a performance study on our AMD ROM clusters, which are state-of-the-art AMD CPUs. And we will discuss the communication impact between distributed TensorFlow and Horovod that Rocco has presented earlier, which is very thankful for me. So I will not have to talk about it again, since we had a great presentation of it earlier. So quickly, I will introduce you the setup that we are using here. The main interesting thing is that for these experiments, since they were really preliminary one, we used a relatively small network, which is ResNet 56, and a really small data set, which is CIFAR10. Because the main idea here was to explore what CPUs can do with AI workloads, with simple AI workloads, and how we could run it efficiently on modern HPC clusters and CPUs. So the first thing that we tested is the binding, because as you may know, modern CPUs have a really complex hierarchy of cores and memory. So here you have a node with two cores here, one core and another core. I don't know if you see my my mouse or not when I'm showing.
It works.
Yes, it's
We
okay.
see the mouse. Yeah.
Okay, so nice. So you have 2 cores, and in each cores you have 4 packs of cores, which X 3 cores and an L3 cache of memory, packed by 2, and then packed by 4 to form a core, a global CPU. So you have a lot of solutions to actually bind your processes onto such nodes. You can use one process, one TensorFlow process per node, for example. You can use 2 processes per node and bind one of them on each core, on each NUMA node. You can use 2 of them in each NUMA node, and so on and so on. So we tried all these bindings to check which one was the better for performance for this experiment. And I think that you begin to understand our point of view, which is really HPC-like, to look at performance and at how you can use the hardware at its most efficiently for our applications that we tackle. So on these applications, we had these results. So here you have a simple table with the average step time for each type of binding with TensorFlow and Horovod, with distributed TensorFlow on 2 nodes, which is really small. But this was our first attempt to run a distributed TensorFlow. So we needed to do it on a small number of nodes. So we see something that is really interesting here, is that we have the better performance per step for TensorFlow at half NUMA, but for Horovod, it's at full NUMA node. So 2 different bindings. But it results that in practice, the best run is obtained with this binding on these CPUs. And as Rocco said earlier, it is because even if the step time is lower for Horovod with a full NUMA node, the quality of the training is not the same because the number of process used is not the same. And then you have all the problematics that Rocco already talked earlier about the quality of the training, the degradation when you use a higher number of processes, etc. So to show you how it looks like, I plotted with a TensorBoard the accuracy of the training of this neural network for TensorFlow and Horovod with 2 point of view. The first is the accuracy by number of steps. So you have here in the x-axis the number of steps, and the y-axis the accuracy obtained by the training. And you see that here it's the gray curve here that has the best performance by step, the best that gain the best accuracy by steps. But when we look at the same graph, but in the x-axis here, you will have the time to target the accuracy. So here you see that the graph is really different. You still have the gray curve at the best here with the full NUMA, which is not that far for 70%, which is the target for the training of this network. But for Horovod, we have a really different behavior. For Horovod, here again, we are in the curve where we look for the quality of the steps. So here you see that it is the CCX binding, which is the one of the finest binding that we have for our CPU nodes that seem to be the best. But when we look at the execution time, at the time to solution, we see that this one is not the best. The obtained accuracy at 70% is the best for, again, the half NUMA binding here in orange. So you see that even if the execution time of a step is better for a specific binding, it doesn't mean that the time to accuracy is the best. Again, because of this problematics of distributed AI learning about number of processes that degrades that have implications with the learning rate and so on. So this is something that you need to keep in mind, that when training a network on distributed computers, you need to take care both at the raw performance of the training of each step and at the quality of the training of each step to be able to have the better performance on your clusters. And finally, I added a small comparison between Horovod and TensorFlow with the same graphs. So here in quality, so you see that for the time node accuracy, it's almost the same, but for the expected time, you see that TensorFlow, the distributed TensorFlow flavor, has a way better performance at 2 nodes. And we try to investigate that point. And we saw that, in fact, when scaling up to 16 nodes, the performance of TensorFlow greatly degrades. This is explained by something that Rocco already said, is that TensorFlow in its version 2 has no support for MPI and globally for HPC interconnects. So that means that the communications is done by the parameter server model of communication and is done by TCP, which is really bad in terms of performance when scaling with such interconnects. So since Horovod uses MPI and so can use these interconnects, we have better performance with Horovod. But after some experiments, we expect that TensorFlow would have better performance than Horovod if TensorFlow had a support for HPC interconnects, because TensorFlow had some optimizations that it implemented, which name its scope allocator. I won't enter into details in this presentation because of mainly of lack of time. But if you're interested in looking at scope allocator for TensorFlow, you will see that they have done some interesting things which really look like the tensor fusion of Horovod inside of TensorFlow, instead of the distributed TensorFlow part of TensorFlow, and currently makes it for the versions that we tested on our experiment, we showed better performance than Horovod. So that was for all the experiments that we mainly made on CPUs. So the key points to remind when you want to run AI workloads on CPUs is that you need to take care of the binding of your processes on your CPUs, because depending on the hierarchy of the processor that you use, the number of processes of TensorFlow processes that you need to spawn on each node and which binding you need to use may be different to achieve the better performance. Like Rocco said, the batch size is really important to also achieve the better ratio between performance and accuracy. And finally, a not well-known parameter inside TensorFlow, which is the number of executors. Actually, TensorFlow spawns the specific number of what they call executors, which will perform in parallel the work for a specific process of TensorFlow. For example, if you spawn one executor with 12 threads, it will use 12 cores. And if you spawn 2 executors with 12 threads each, it will use 24 cores. And we saw a great difference in terms of performance when using this parameter wisely. So I show you here the example. I won't enter into detail, but when we made a comparison between when we run this training at the beginning of our work, it took around 30 minutes. And at the end, it took only about 7 minutes. So with careful binding and careful, how to say it, by taking care of the parameters wisely, you can achieve a big speed up in CPUs also. So CPUs are not the best architecture to run AI workloads, but within that, with proper binding, you can use CPUs to run AI workloads at least decently. So that was it for the CPU part. Now I will talk about our GPU experiments and specifically about our I/O concerns. So on GPUs, the goal was mainly to identify if our GPU clusters would be competitive with NVIDIA's DGX, especially since we at Atos have GPU clusters with NVIDIA 800. So we wanted to assess their performance and to see whether they were competitive. And we really looked at the I/O capabilities needed to correctly fit those GPUs, because 800 are way more powerful on AI computations than the previous generation. And then we began to see some problematics about how to fit them correctly, especially when on a single node you have several GPUs, like for example in Summit, like you have 6 GPUs per node. So you need to be able to feed all the 6 GPUs at the same time, and your I/O support need to be able to provide this this bandwidth. So again, I'll show you quickly the hardware that we used, but the interesting thing here to retain is that we have 4 800 per node, and here we switch to the ResNet 50 training on ImageNet. Which was the second part of our experiments. We switched to a bigger AI workload to be able to evaluate the performance on modern GPUs. So for our results, we didn't have many nodes with 800, like the one showed by Rocco. We only have 2 nodes. So with our 2 nodes, we were able to show that we achieve competitive performance with the NVIDIA blades. But like Rocco said, NVIDIA's displays 8 GPUs per DGX blade, and all these GPUs are interconnected through the NVIDIA's NVLink, which has a higher bandwidth that greatly higher bandwidth that HPC interconnects. So that is why you have a slight delta here between the result presented by NVIDIA and the one that we obtained on 2 nodes, because the interconnect between the 2 nodes being an HPC interconnect instead of NVLink, the interconnect is slightly slower. But we are really happy about that, and this shows that we can run AI workloads on such blades with almost no efficiency loss. So we need to experiment at scale, and this is one of our future steps on that topic. And finally, the last thing that I will talk about is about the I/O, because we, like I said, we saw that 800 were eating a lot of images per second, and we wondered if the current supports for I/O in the HPC machines were up to the task. So we evaluate the 3 classical I/O that you can find on HPC cluster, which is NFS, SSD, and NVMe, and we evaluate them against a RAM disk, which is software that emulates a disk inside the RAM of your machines, which gives a greater, highly greater bandwidth than SSD or NFS. So the idea here was to check if one of the or several of these supports were slowing down the training of AI workloads or not, depending on the condition. So to do that, we made 2 experiments. The first one, when the dataset can fit in the RAM of the machine, which was the case for ImageNet in our case, which is 144 gigabytes, if I remember correctly, which fits in one of our nodes. But we also evaluate the case where dataset cannot fit in RAM, where you have terabytes of datasets to input to your neural network to train it. And to do so, we emulate a node with only 50 gigabytes available to force TensorFlow to reload again and again at each epoch through I/O the dataset and see whether it causes a performance loss on such machines or not. And
Marc, we lost you. We do not
Yes.
hear. Yes.
Same here. You maybe came to the mute button or so.
Yeah. I'm not sure he's. I will ask him in the chat. He is not connected.
oh, I'm sorry. Do
Cool.
you hear me?
Yeah, you're
we
back
hear you.
again.
Yeah,
Yeah,
I had
very
I was cut because my my headphone had no battery anymore, so it's okay. I will try to finish it quickly. So what we saw in our results is that while only the NFS was not slow loading the data at the first epoch for our training, and then afterwards, since the dataset is in RAM, it shouldn't it hadn't to load it again and again. So all the other epochs were behaving well. When the dataset cannot fit in RAM, you see that you have a great impact when loading the data from NFS, but also with modern SSDs. So we saw that we saw a slowdown pretty noticeable on all epochs of the training with SSD and NVMe, which led us to think that users need to take care about where they put their dataset to train their AI workloads on with modern GPUs. And while modern GPUs will keep up increasing in power, we think that AI workload training users should be wary about how the I/O level can correctly feed all these computing resources efficiently so that the GPUs can be used at full power. So I'll go through this very quickly because I think I'm late due to my disconnection. But we have other ongoing efforts on our team to use AI for example, to tune OpenMPI and our users' SPC applications with a PhD thesis on the subject. And of course, we collaborate with Gael and his AI for Sim team on this project, mainly by providing our expertise on distributed AI runtimes that I showed you some today, and I hope to be able to show you more on next month and years. So thank you all. And if you have any questions, I don't know if it's now or later.
Yeah, thank you very much, Marc. That was very interesting. I think in two ways. Firstly, to really think about that companies, of course, in startups, they not can afford A100s in the extreme high scales all the time, right? So they still have CPUs at their disposals. And the second takeaway message is really thinking about more I/O when you think about scaling in GPUs. While HBM is helping, I think still there needs to be lots of things done exactly when it comes to feeding, as you actually worded it, feeding the GPUs with meat, with data in the area, especially when we think about Exascale. So there the question is how we bring this data together. But thank you very much. I would say if you have questions to the audience, please feel free to put them in the chat. I would invite Marc to answer them in between already while we move to the next presentations so that we don't run out of time. Also, the ones that are put in the chat, we will follow up with Rocco. So just as a reminder, also Rocco, if you have still questions to his talk, feel free to use the chat. Otherwise, I would say thanks again, Marc, to present and also being available later for questions. Marcel, I think now we have a next speaker that I failed. Okay, I think, yep. We lost a couple of people, unfortunately, in that. But as it is actually recorded, I think we can go ahead and see as the people will join in the meantime. So Marcel, thank you very much. Maybe shortly you can introduce yourself, as I forgot it on my slide, because you chipped in last minute, so to speak. Please shortly introduce yourself and then go ahead.
Sure. Yeah, hi everybody. I am Marcel Aach, And since May, I'm working jointly working as a PhD student from the University of Iceland at the Jülich Supercomputing Center, and I'm supervised by Morris. So what I want to talk about today is a bit about the experiences we have made with a few deep learning frameworks, and especially show you some benchmark results we achieved. So as Rocco and Marc already mentioned, there are a lot of different frameworks. DeepSpeed, Horovod, TensorFlow, and even PyTorch have their own distributed deep learning frameworks now. And now the question is, which one, when you want to do distributed deep learning, which framework do you choose? And the two important metrics we're looking at is first the parallel efficiency. So how good is the framework actually able to scale up across a huge number of different nodes? So is it actually worth it to use more GPUs for training, or is it just a waste of computing power and the GPUs are just idling? So that's the first thing. And the second thing is, of course, the accuracy, because if your framework scales very good, but cannot achieve good prediction accuracy, then of course it's worthless. So that's the second thing you have to look at. And the valuable HPC systems we have here in Jülich, I shortly want to introduce. And the biggest one is the new Jülich booster, which features more than 900 nodes, each equipped with 4 NVIDIA A100 GPUs. So this is really state of the art in terms of technical equipment. And we still have the Jülich cluster, which features around 60 nodes, each equipped with the older NVIDIA V100s. And then there's also the deepest extreme scale booster, which also has another 17 nodes equipped with NVIDIA V100s. So the two main frameworks we focused on are Horovod, which was developed by Uber 3 years back in 2017, and it can run with lots of different deep learning frameworks with TensorFlow, PyTorch, and some more as well. And then there's this new thing, which is the PyTorch distributed data parallel, which is only about 1.5 years old, probably. And since it's from PyTorch, only runs with PyTorch, of course. And the use cases we're looking at so far have been only convolutional neural networks. One project we have here in RAISE is building up an autoencoder, which of course features a lot of convolutional layers, but also some residual networks and networks with shortcut connections. And here you see, for example, from the autoencoder, a small sample images where we are trying to predict the flow on a turbulent boundary layer. And so far, we have not been looking at transformers or language models, which is why we're only focusing on these data parallelism right now. So no model parallelism is happening yet, at least in our group. Showing you a result of a benchmark, this time the ResNet 50 applied to the tiny ImageNet, which is a smaller version of the original one, just to see how well these two frameworks perform on a standardized benchmark. And what we can see here is that this DDP from PyTorch has a very, very good efficiency. So even scaling up to 256 nodes, which is, so we have 4 GPUs per node, which is like 1,000 GPUs, we still get a very, very high efficiency, which is of course very good. It's close to the ideal efficiency, way above 97%. And we see that actually Horovod cannot really keep up with this. It's like maybe until 4 or 8 nodes, it keeps close to 90% efficiency. But once you go further, the efficiency just drops, and I didn't even run it on the larger, but we would probably see the same results there as well. So benchmarking the accuracy, we can here see that for the PyTorch distributed data parallel, we can basically confirm what Rocco already told us. So this is just a simple ResNet 50 with no LAS optimizer and no learning rate warm-up. Only the batch size is scaled per GPUs, but that's it. And this is the test accuracy, so on unseen data. And we see that while for up to 8 nodes, this remains above like 60 to 70%. Afterwards, once we are actually moving to these batch sizes of 8,000 samples or more, we see that the prediction basically just falls apart and goes way down. Unfortunately, I couldn't show any Horovod results here because these were also not that consistent. So that remains something that needs to be investigated in the future, how DDP accuracy actually compares to the Horovod accuracy. So let's investigate a bit more with this DDP package. And these are plots that were obtained from an actual application, the autoencoder I just mentioned, so not some benchmark. And yeah, this also confirms what I have just shown on the first slides, that the scaling up to 256 nodes is very good. It's almost equal to the ideal speed up. And also the parallel efficiency. If there are some fluctuations here, but we can see it's well above 97%, so that's also very good. And for the training error, we can also see what Rocco mentioned in part, that once you move to a bigger number of nodes, the error actually increases. This is with like a scaled with a fixed learning rate. So once we actually move to a scaled learning rate, we can see that while the training error actually in the first nodes is higher, that once we move on to bigger nodes, the bigger number of nodes, the training error decreases. So this seems to work. There's also some fluctuation happening here on the big number on the 256 nodes, but still, yeah, we see that the error actually decreases, and it does not seem to have any effect on the efficiency, of course. So these benchmarks were always done with this Nickel backend, which is the communication library provided by NVIDIA. And if we compare that with the MPI backend, which you can also run DDP on, you see that this has worse efficiency. So this apparently introduces some overhead, which causes the efficiency to drop down below to lower than 80% for even 32 nodes. So let's take another look at Horovod. And this, again, for the autoencoder case, so not the ResNet benchmark, but like a real application. And what we can see here again is that this is just confirming the results I have shown on the slides in the beginning, which that with an increasing number of nodes, Horovod cannot keep the efficiency that high, and it drops quickly. So some finishing key takeaways. So far, the results have shown that Actually, DDP seems to be faster than Horovod. We still need to confirm whether this also holds true when we look at the accuracy. Also, I haven't found any good explanation yet why that seems to be the case. I read in some PyTorch forums that DDP is actually better in overlapping communication with the backpropagation, and Horovod apparently cannot do this. If you use DDP, you should use it with the nickel backend, of course, when working on NVIDIA GPUs. It's worth to mention that, at least from my perspective, Horovod is a bit easier to use. It's just maybe 5 lines of code you have to add to your neural network, and then it basically works. DDP is a little bit takes a little bit more effort, and of course, it is important to scale the learning rate with the number of workers. Yeah, that's what I had to say so far. Thanks for the attention.
Yeah, thank you very much, Marcel. I think you enriched this perspectives we had before very much, also in the order of scaling, really. And I think what we discussed in the beginning, just throwing GPUs at a problem will not help you, as we see with the batch sizes, right? While there are new optimizers that can deal with this, I think it shows you very nicely that the scaling towards Exascale is really research, what we do and conduct here in CoE RAISE along the lines. And of course, we have still something not really touched if you think about that we now have nickel and we have NVIDIA, but we're going to a future where we have heterogeneous GPUs also. So that means a lot of other things what we have to explore. How good will be these frameworks with non-NVIDIA GPUs, which will come around. So I think there are lots of other issues which really makes it an interesting research endeavor. But thanks again, Marcel. I would invite also to have just a couple of questions in the chat if you want. We do a couple of minutes longer. Maybe if you allow me to share my screen,
Sure.
Orbit, then I will just, wrap up this. Again, please put it in the chat if you want. We will follow up on this. I just give some closing remarks and of course a sneak preview again to our next seminar, which will happen then in August. First of all, thanks for joining. I hope it was interesting for you. We brought together as much experience in the moment as we could on CPUs, on GPUs, and so on. So if you want to know more about RAISE, it's Rémi, could you please mute the microphone?
Normalement, début septembre, je suis censé changer de bureau. On va récupérer les bureaux de...
I think I could do that even. Good. So yeah, good. If you want to have more information, please go to the RAISE website, what RAISE is doing. I think this is clear. Today, we will have really just a glimpse of what we do in CoE RAISE. There will be much more interesting things when we dive into each of the different models. I think Marcel had a very good point, ResNet 50, and there's also the autoencoders. So there's much more when we think about the real complexity integrating all of these models. And then we have to check the accuracy if that will hold. All of the different problems we have in RAISE are truly different. So we have to really think about how we deal with this when we think about also the tasks we have in CoE RAISE with this unique AI framework. But today we got some, I think, good idea of sharing our experiences. And if you want to know more, the basically YouTube channel of RAISE gives you seminars that we had before. So also HEAT was another framework we looked at, which has some ideas to offer. In the moment, we're installing HEAT, we're installing even DeepSpeed, we're installing Horovod, we're installing PyTorch, and look and run all of them and try as best as we can. DeepSpeed was a little bit problematic in installing. I think that's what I can share right now. So otherwise would have maybe also already shared something. It's completely different from the usability perspective than Horovod, where you essentially just have a couple of lines of codes added and it works like a charm because it has been used so much in the last 3 years. So we see also there, of course, the technology maturity matters a lot. And during the course of the CoE RAISE project, we will make sure to cover these technologies. When we have more insight about DeepSpeed, we maybe do another seminar on DeepSpeed. So maybe it's good to subscribe to the YouTube channel here from the CoE RAISE project to stay informed if you want. And also this seminar will be appearing there. We have to check here and there with confidentiality issues, of course, given that we have also company presenting today. But other than that, I think the YouTube channel is a very good source. Speaking of AI models, what comes next? When we were going with the interaction room and with the fact sheets for all the different use cases in CoE RAISE, we clearly saw that the autoencoders are a model of AI which actually matters in some of the different use cases. So we will have a dedicated seminar in August providing some ideas what an autoencoder really is. I mean, you have seen in Marcel presentation a little bit kind of the turbulence, which was, so to speak, then recreated out of this autoencoder, but what it really is and how it works will be the idea of the seminar in August. Of course, we will do this in the context of HPC, so we will also not only capture, let's say, the mathematical basics of an encoder and decoder technology idea, or basically model idea if you want. We also will look on how that really scales on different, let's say, HPC resources like Marcel already shown today, and where it is used. So one example you see here, for instance, in remote sensing applications out of my own research, just as a very simple example, where it's basically the compression here of one of the hyperspectral images we have in remote sensing, where you have basically a nonlinear data compression going on in this encoder element and basically come to a very, let's say, compressed representation of your data. And this could be helpful for many things that we will also touch on basically in the seminar. But of course, you have here also one publication, or basically join us then in the next August seminar, because then we will also see how that will be used with other use cases. We will share some practice experience really working with those on our HPC machines that we have available in CoE RAISE, and how you can maybe map some physics problem down essentially to an AI problem that we have seen with the turbulence, but will be coming much more in detail, of course, in the August seminar. There's no date and time yet. It will depend on the invited speakers that we have. But if you basically keep in touch with RAISE and maybe subscribe to the Twitter channel in RAISE, you will also get updates, or LinkedIn, wherever you would like to prefer to read from us. So in this, we really conclude the seminar right now. We lack a little bit the discussions given the problems, but I see also in the chat not many questions. But feel free to contact us at CoE RAISE if you have more questions about this topic. And my final thanks go, to, of course, to the invited speakers, to Marc, to Marcel, and also Rocco, although he couldn't make it in person. And yeah, would love to see you again, basically in the August seminar. Thank you very much for your time joining. Bye-bye.
Thank you. Bye.
Thank you. Bye.
Thank you. Bye-bye.